So still looking at shapes with circular cross sections. So exactly the same as everything we've seen before, but now a different way of approaching it. So traditionally, certainly from 2 and 3 level, we take those slices perpendicular. But what if we took the slice parallel instead? What would happen there? Now, let's go to our random shape there. So same volume we were investigating there. We want to find the volume of the shape when we rotate between A and B. So I've got my slice parallel to the rotation. And when we rotate that single slice there, we end up with a cylinder with a hole in the middle, if you like. That's why it's called a cylindrical shell. It's a shell of a cylinder. Personally, I find it easier to think of it like you're peeling off layers from the volume. And so as you peel it off, you create like a rectangular prism, depending on how thick your peel is going to be. Or another way of thinking about it is just cutting the cylinder there and unravelling it. And you'll end up with a rectangular prism rather than a cylinder. The thickness is still delta x, of course. The height of my cylinder, which becomes my rectangular prism, is going to be the y value. But again, I want that in terms of x because the thickness is in terms of x. So it'll be whatever function x is. Now the width of my rectangular prism will be the circumference of the circle. So it'll be 2 pi times the radius. And in this case, the radius, the rotation is at the y-axis. So if we go from the centre of rotation to the slice, it's just simply the x value. So we get 2 pi x. So if I multiply those two things together, I get the area of my rectangle. 2 pi x times function x. Now, some books will just quote that, 2 pi x. Well, I actually see it sometimes written as 2 pi xy. Which is fair enough, that's what it turns out into. But do not just quote that. Later I'll show you why. But. So to get our element of volume, we get delta V, 2 pi x, function x, delta x. So everything is in terms of x. And then it becomes the same as yesterday. Now we're just summing up. So it's a bit like, you know those, what do they call them? Is it babushka dolls? You know, as we go on, so it's a bit like that. You end up with a solid, but you're taking out layers of cylinders, if you like, and we're adding all of those up. So this integral, again, we can factorise out the constant, so we can factorise out the 2 pi, and it'll be x times function x we end up integrating. So let's do the same example as yesterday, so we can see that we do get the same amount. Upside down parabola, you remember we had yesterday, we're going about the x-axis. So my slice is going to be parallel to the x-axis. So when I rotate that one, there's my cylindrical shell, but I'm going to unwrap it. The thickness is delta y, so the change in the y value. The width, in this case, because of symmetry, the width of my prism here is going to be 2 times the x value, so x on either side. And I'll need to rewrite x, so x will become the square root of 4 minus y. But obviously I've put that in index form. Now, the height of my prism will be 2 pi times the radius. In this case, the radius is the y value. So I've got everything in terms of y, so that looks good. So I can say, well, the area of the cross-sectional face is 2 pi y times 2 times 4 minus y to the half. Multiply that by delta y to get our volume element. And that's what we'll end up integrating, because that'll become, we're going to sum all of those. And remember, it's y values I'm dealing with this time, so I'm going from 0 to 4. And that's what we have to integrate. Not quite as straightforward as the one yesterday. Yesterday, you remember, it just turned out to be a nice add 1 to the power over the power. Here I've got y times 4 minus y to the half. I can't expand out 4 minus y to the half. Going to have to use one of our techniques that we've seen. But I know which technique I'm going to use, because have a look at the limits. It's 0 to 4. So I can do that nice substitution. So I can change it to be 4 minus y, y to the power of a half. Right? So remember, when it's going from 0 to a, you can substitute in a minus x. So it worked nicely for this one. So now I can expand out, and I do get one that's just add 1 to the power over the power. And sub in, and we get, thank goodness, the same answer as yesterday. So that example is, I'm not saying you would do this one that way, but that's just to show you that the method would work. Clearly the discs would be an easier way for doing this question. Okay, let's try this one. We're going to rotate the circle about the line x equals 4. All right, there's my circle. We're going to go around x equals 4, and when we rotate, we'll get a wonderful shape, or I should say solid. Yes, something we should recognise. But there's my slice, delta x. It's going to rotate around. Now, if I was to do that to every slice, let's try and create the shape. A bit hard to do it, but perhaps you get the thing. It's a donut. Okay. So if ever you're trying to work out, I wonder if he's got more donut in his donut than I've got in my donut. You could work it out. Just slice it, find out. I told you, maths is useful for everything. Yeah. Okay. Okay. Technical name is torus, by the way, not donut. Let's unwrap our cylinder. Okay, we want everything in terms of x here. So the height, again, I've got symmetry, so it'll be twice whatever the y value is. But I want that in terms of x, so that'll become 2 times the square root of 4 minus x squared. Now the radius, where are we? Well, centre of rotation is 4, so it's going to be 4 minus whatever the x value is. So we get 2 pi 4 minus x. So the area, okay, let's tidy it up. There we go, 2 pi 4 minus x root 4 minus x squared. So my element of volume, multiply that by dx. We want to sum all of them. Remember, the sum is just the circle. It's not the whole thing going to 4. So we're going from minus 2 to 2. There's our integral, which looks horrid. But it actually is fantastic. Watch what happens. I'm going to split that into 2 integrals. The first one becomes 4 times the square root of 4 minus x squared. The second one is 4x times the square root of 4 minus x squared. Now, watch and be amazed. That's a semicircle. So I don't need to integrate. I'm just finding the area of a semicircle. So 16 pi times a half of pi r squared. But look at the second one. It's an odd function. Odd function minus 2 to 2 is 0. There's my answer, 32 pi squared. How cool is that? Okay, now, so throw in some more there to do.